Welcome to Ask and Learn.
So in this problem, we have a block that's going down a ramp at a certain speed, and it collides with the spring, compressing it even further. So we want to find the velocity that this block has as it's going down this ramp. And we'll call that V1. So we're given the stiffness of the spring. That's 50 pounds per feet. We're also given the weight of the block, which is 4 pounds. And we can convert that to mass by dividing by 32.2 feet per second squared. So the mass is 0.12 kilograms. And we're also given coefficient of kinetic friction because the block experiences friction as it's going down the ramp. So for the coefficient of kinetic friction, we have 0.2. So to find the velocity, we can use the work energy principle, which is the initial kinetic energy plus the work being done by all the forces involved will equal the final kinetic energy. Well, we know when the block strikes the spring, it'll stop moving at that moment. So the final kinetic energy is 0 because the velocity at that point is 0. So now we're left with initial kinetic energy, 1/2 mv1 squared plus the work being done by the forces will equal 0. And now let's look at the work being done by the forces. So if we think about it, we have the force of the weight of the block, we have the force of the spring, and we also have the force due to friction. Okay, so now let's think about the work done by the weight. So it's sliding down the ramp. So we have the weight in the x direction times the distance it travels. So this block is going to travel 3 feet plus the length of the compressed spring after it collides, which it compresses 0.2 feet. Okay, that's for the weight. Now for the spring, the force of the spring will push the block in the opposite direction, so its work will be in the opposite direction as well. So we have 1/2 parentheses 1/2 k s1 squared. So S1 is the length of the compressed spring before the collision. So S1 will be 2 feet. That's the length of the unstretched spring minus the 1.5 feet it's compressed, and that's squared, plus 1/2 k S2. That's the length of the compressed spring after the collision. So again, the length uncompressed is 2 minus, so before the collision it's 1.5, but then pushed down another 0.25. So this is 1.25. That's squared. Okay, now the force due to friction is in the opposite direction of the motion as well. So that's minus mu k Fn times the distance, which is the same as the block. So it travels 3 feet plus the length of the when the spring is compressed further, which is 3 plus 0.25. So what we don't know is f of n and the weight in the x direction. So we're given a nice little triangle so that we can find the components. We have 4, 3, and we have 5. And if we draw a free body diagram of this block, we have the weight straight down, and we have the y, wy, and we have wx, and in the opposite direction of w, we have fn. So from this diagram, we have fn is equal to wy, which is w from the triangle times the ratio 4/5. So if you plug in for w, for the normal force Fn, we get 3.2 pounds. And the weight in the x direction, we have w, and from the triangle times the ratio 4/5. So now if we plug everything in for our equation for work, we have 4 times 4/5 times 3.25 minus 1/2 k is 25. So if you take out the 25, you have 25 times parentheses s1 squared plus s2 squared, so 0.5 squared plus 0.75 squared, and then minus the work being done by the friction, so 0.2 times 3.2, the normal force we just found, times the distance it travels, 3.25. So the work being done by the forces is minus 2.09 joules. And now we can plug this in to our first equation. And we have, for the initial kinetic energy, 1/2 times m, 0.12 times v1 squared, minus the work we just found, 0.2 minus 2.09. And this is equal to 0. So we're solving for this velocity, v1. So we have v1. So let's move 2.09 to the right, and then this whole thing divided out over there. So we have 2.09 divided by 0.06, and to get rid of the square, take the square root. So the velocity that this block travels down the ramp is 5.9 feet per second.